multiple presidents to cycle through each year if we don't have, if no outcomes. Yeah. All right, I think we should probably start.
I think that's a good idea.
Apparently we have two viewers,
Excellent.
participants. Okay, apparently not. It's just us. Oh well,
Oh,
let's just start anyways. Hi Google. Bye Google. Nice. Okay. I think I'll probably start off with this one. So, hello everyone. I know there's none of you here at the moment. That's totally fine. Also, by the way, I'm presenting the slides. I probably won't be able to say. Actually, that's a good point. Seamus, could you go to the stream and have chat up so when people ask questions, you can tell me because I can't see chat right now.
yeah, no worries.
Cheers. So, as you've probably ascertained, I have our illustrious Vice President Seamus here helping me present because, gosh, string algorithms are hard and not my strongest bit. But they're still very, very, very important, and we're going to go over why. So, what are string algorithms? Well, pretty simply, they're algorithms that do stuff with strings. I know that's such a great definition, but the most common one you're going to find is pattern matching, and they turn up absolutely everywhere. They turn up almost every good competition will have some kind of string algorithms question or something that's related to strings that's kind of badly disguised as a string algorithms questions. And the the kind of trap people fall into when you're dealing with strings is that it's very easy to describe to prescribe derive. Sorry, yeah, I'm really not doing well on the talking front today. It's very easy to derive naive or brute force solutions, but it's much, much harder to do better than that. And that's what we're going to cover today. Some of the algorithms going all the way from n squared down to linear time. So, just as a quick introduction, the naive solution is brute force. You just start at every point. You check every, what we're going to call a shift, which we're going to come off later, and that's you start at the first character. Compare your characters, see if anything works. If not, move along to the next character. See if it matches. Move on to the next one. See if it matches. And that seems like a pretty logical way. You just check every possible place that you could fit your pattern string into your overall text. But as we're about to see, we have much better solutions available to us. Now, I know some people in the audience are probably going to be thinking, yeah, these string algorithms are cool and all, but where am I used? Surely this is just implemented in some library and I chuck it in a big fat juicy import statement. And the answer is yes, you probably will bring it in a big fat juicy import statement. But the thing is if you're wanting to build things that are really, really highly performant, so regular expression matches, a lot of bioinformatics and gene sequencing, compression algorithms, string algorithms are absolutely paramount. You cannot escape them.
Just as a sort of side note to that, if you ever try and build a compiler or a parser, string algorithms are essentially all you do.
That is a good point because when you're building the Lexa, everything's string algorithms, and you're just
Yes,
parsing a grammar with regular expressions. It's
yeah.
gnarly stuff. So we're just going to cover a little bit of terminology just to start off. So I've thrown around a fair bit of it already, but just in case you're not on the same page, a string is an array of n characters. Char or character is a standard data type in ANSI C and pretty much every programming language. Even Python, JavaScript have their own notions of what a string is as a data type, and Java and C++ have perhaps better containers than raw C, and that's just simply a character. You have your 8 bytes, which is your character, and you just have an array of characters. We normally, so most of you will all be familiar with our standard alphabet. In string algorithms, some string algorithms questions, we will restrict the alphabet to just be a certain specified set of characters. It won't always be the alphanumeric characters. Sometimes it might be alphanumerics and numbers. Sometimes it might be just a set of symbols. So alphabet is important, and there's a lot of gotchas if you don't read what that is correctly. You have a substring, should be pretty intuitive in that you just take a piece out of a string, that's a substring, and you have a subsequence. So subsequences are very similar for strings as they are in arrays. It's just you select elements that aren't necessarily contiguous to each other. And as you'll see on the slides, there are very nice fancy mathematical tricks for deriving exactly how many substrings and subsequences there possibly can be. And if you were here for last week's number theory session, you might be able to derive some of those results from combinatorics. The next thing we're going to get in... Yes, Seamus?
You might want to be mindful about how much the camera is covering as well. So if you're not using your paper, maybe just minimize the camera.
Yeah, that's probably a good idea. Oh, true. Yeah, that's very valid. Is that better?
Much better.
Cool. Yeah, apologies for that. OBS does... I need to get multiple monitors so OBS can actually do OBS better than it's currently doing. It's a bit of an issue. So now we're going to move into the more string-specific terminology, in that you won't see this terminology really used anywhere else, in computer science at least, like period and border and lexicographical order will be used elsewhere, like in wavelengths and stuff, but mostly for strings. So the period is just a prefix such that the string is constructed by repeating the period. So we haven't covered what a suffix is yet. Did we cover? Okay, sorry, I skipped 2 slides. My bad. I definitely don't. I'm not just randomly pressing the arrow keys and hoping it works and have a clicker instead. So we have a prefix. So that's just a substring that starts at the beginning of the string and goes n characters into it. If you have an n character prefix, you just simply have the whole string, but the key point is it must start from the first character. You then have a suffix, which is the same as the prefix, but it starts from the last character in a string. And there are a lot of really gnarly, cool properties you can gain from getting prefixes and suffixes that are sometimes overlapping, mostly non-overlapping. You then have what's called a rotation. So if anyone's done Caesar ciphers or general ciphers in cryptography, you know that rotations are a big cool thing because you can rotate the alphabet through. There are algorithms to deal with that, and so all that means is you take the last character of your string, you chuck it on the front and call it a day, and you can do that however many times. The last one there is what's called a shift, and this is more specifically applying to algorithms in that it's just the position at which you start your comparisons or you start your algorithm at. So if I wanted to take the example string ABCD, a shift of 1 would just mean I start at B. And normally I will, for the first few algorithms, I will phrase solutions in terms of shifts. So you will have a shift or a match at shift 1 means that if we're looking at the paper here, so if we have the string A, B, C, D, and I wanted to match the string B, C, well, obviously we do have a match here, but that's starting at a shift of 1, because we've shifted our starting point over for 1. The next thing is we're going to have what's called a period, so it's just you're constructing your whole string out of repeating units. Those units just have to be prefixes though, and not very many strings are entirely periods unless you just take the trivial case in which the entire string is a period, but it's some very interesting things that come up with that. And then you have a border, which is a really cool thing, which in that the prefix and the suffix are the same, in that you have the same sequence of characters at the beginning of the string as you do at the end of the string, which for some of you that might be somewhat reminiscent of a palindrome, which there are definitely a lot of algorithms to that, but we will not be covering those today. The last bit of terminology is lexicographical order or lexicographical order, however you want to pronounce it. This is just a really big fancy word meaning instead of ordering it by numbers, order it by letters, where A goes to Z and A is greater than Z. Or that's one interpretation, or another interpretation is using prefixes. Because I didn't read the dot points and there's multiple interpretations.
Yeah, so basically what these dot points are saying, if you, they're essentially defining the algorithm for lexicographical order. So X is less than Y, if by character comparison from the start of X and Y, the first instance where the letter of X is less than Y or the letter of Y is less than X, we base our ordering on.
Yeah, which makes a good deal of sense. We won't be covering that algorithm today. So to start off, we're going to cover the naive method of string matching, and that is just simply take our pattern string and check every possible start point for comparison. So in this particular example here, let's start at the first character of both. Does C match A? Nope. Does B match D? Nope. Cool. We shifted along by 1, so we're now at a shift of 1. Check it again, doesn't match. Shift along again, we're at a shift of 2. Doesn't match. We shift along for the last one, we get a match. So in this case, we have shift of 0, shift of 1, shift of 2, shift of 3. Shift of 3 is a match, so we would return 3 as our match, or the point at which the string at which we will get a valid match, which is pretty cool. The thing is, with this method, well, actually, no, sorry, here we have put some code in first, so it's very simple. It's just a double for loop. So for each possible shift, and so you'll notice here that we're not going over the entire string because we have to take into consideration that after a point, you can get just overlap over the end of the string. So if you went to the end of the string and said, hey, I have 3 characters left in my string, but my pattern is 5 characters long, well, logically there just isn't possible. It isn't possible for there to be a match there. So that's why we have the this particular statement. Nope. So what we do is we check every possible shift. We assume that we have a match and just have to compare the bits of the string to see if we actually get to keep that match. And most of the time that match is going to come up as false, but if somehow we've matched every single character, we have a good shift, we simply add that shift to our results and continue on to find every single match in our target string. There's no real reason just to stop at the first string because the worst case complexity is always going to be the exact same, so you might as well get free information and find all possible matches at every point. Looking at the analysis, so I'm using n here to represent the length of the input string, and I'm using m here to represent the length of our pattern, or the pattern that we're searching for. And as we've said before, there are n minus n plus 1, because we're starting at a shift of 0, possible shifts, so we can move our character along n times till we don't have any more characters left to possibly have a shift. And because each time we have to check the length of the pattern at each possible shift, we're getting m times n minus n plus 1 for our overall complexity. So in general, that's effectively going to give us an order of roughly n squared in absolute asymptotic case, because that's just the worst case in this particular thing. And the next logical question that you probably want to bring up from that is, where can we improve that? Well, the naive method fails at 2 points. Number one, it fails in the shifting process. If we analyze the first shift, we've gained a lot of information about our target string already, and by moving on to the next shift and not considering, we're just disregarding, throwing away all that bonus information. So we say some such information could include, hey, part of this string matches a prefix of our substring, so maybe we could skip a few characters. Or, oh no, we have a partial match of the string here, but not a partial match here, so you could have skipped more characters instead. So a lot of the methods we're about to come up to are taking more information from the shifts. And the second is the comparison process. we have one string that we're comparing identically every single time. That seems inefficient. So we're going to focus on the comparison process, and we're going to look at the ladder solution, and that is string hashing, otherwise known as the Rabin-Karp algorithm. For those of you who want to Google it, or those of you who want to know where it came from and look up the original paper, would recommend it. It's a good time. So this is really fixing the problem of comparison, because we have one target string that we're always comparing each and every single time. Well, if we hash that to a specific value, say any number, we now have an integer, and we hash our target string or parts of our target string, we now have an integer comparison or a constant time comparison, as opposed to a length time complexity m comparison, which is much, much better. The problem is how do you break up your input string or your target string such that you can compare the hashes appropriately? And this is where we use method of polynomial hashing. So for those of you who aren't aware of polynomial rings or finite or fields and modular arithmetic, I would recommend going back and watching last week's session on modular arithmetic and number theory, because we cover a lot of this stuff here, or most of this stuff here that's pretty necessary. And we're going to go through examples. So you'll see up on the slides here, we're just looking at the string at various we're looking at various substrings or various points of the string, and we're just going to go through an example because that's going to be overall more intuitive. So to start off, what we need to do is we need to represent every single number as, or every single character as a number, and that's going to help us out a lot. We just represent every character as a number, and then we simply just multiply the numbers out. So what you're noticing here is that we have the numbers assigned. In this particular case, the numbers are actually representing the ASCII representation in binary, or in decimal of the binary representation in ASCII of the various letters. So most of the time you even won't have to worry about the numeric conversion, but in this case what we're doing is we're multiplying it by a factor of to the position of that it is in the string. And so what that means is that we're simply ensuring that this string here is unique, because if we had A, L, L, E, and we just added up those numbers to represent our hash, that hash would be exactly the same as if we did L, A, L, E, because we're just adding up the same numbers. So what we do is we take our sum number. In this case, we've chosen 3. We're just going to, for now, just take some number, and for the position of the character in the string, we're multiplying it by that position, the number to that position's power. So I think looking at it on the slides makes more sense than how I'm explaining it at the moment, but we simply just say 65 is in the first position of the string out of a length 4 string, so we give it the most important value. In that we make it 3 to 4 plus 76 to 3 plus 1. So the reason why we're using modular arithmetic here is that we're trying to avoid integer overflow, because multiplying by numbers to powers gets very big very quickly. And if you remember our modular arithmetic session last week, you'll know that we can apply the modular arithmetic at any stage in this addition process, not just at the end, to avoid interval. But that might bring up the problem, as seeing as the integers mod some certain number are cyclic in that they will eventually loop back around and you can get duplicates, that brings up the question of collisions, which we're not going to get to just yet. We're not going to get to just yet because I didn't reorder the slides, but just keep that in your mind. So more implementation specific this time, we're going to talk about the concept of pre-processing. So I'm sure Seamus would have gone over for you pre-computing some DP tables for very nice fun times for answering queries. We're using a very similar thing here in that we're computing a substring table, or in this case a hash table, where we simply store the hash of each substring, so we can directly compare it when we're using our comparison algorithm. It should be pretty easy to read over the slides here in that we look at the first string, we get the first m characters of it, we hash that, then we move along to the next one, hash those m characters, move along to the next one, hash those m characters until we have no strings left. And in fact, this is linear time. We don't have to every single time work it up, because all you need to do is, I'll write this on the whiteboard, is if we have a string A, B, C, D, and we have our values here, so this could be 1 times 3 to the 4, 1, 2 times 3 to the 3.
David, you might want to make it bigger.
Thank you very much. So we're going to come over to the whiteboard here, and please focus camera. Okay, I need to write bigger, that's fine. So if we have our string A, B, not D, C, D, then we represent numbers very simply. We go 1 times 3 to the 4, plus 2 times 3 to the 3, plus 3 times 3 squared, plus 4 times 3 to the 1 for this particular string. Let's say if we wanted to add another character and we were just looking at blocks of 4, well, all we need to do is add this, subtract off this number, and then multiply this entire string by 3, or our number, and that will move it into the exact same position. So we subtract off this, and then we multiply everything by 3. So we get 2 by 3 to the 4, plus 3 by 3 to the 3, plus 4 by 3 squared, plus whatever it is, 5 times 3 to the 1. And that'll get us our hash that'll get us all of our hashes in linear time, which is a very neat trick. Of course, we'll have to keep into consideration the modular arithmetic. As I just said, we can simply take this as ON time, because we're just adding and subtracting each time, which will be constant time operations. And once again, if you're remembering last week's session, programming languages don't implement true modulus, they just implement the remainder. So if you actually want it to be a true modular arithmetic, you need to ensure that your operands are all positive, which is very important. There is, depending on how large you're expecting your bounds to go, you can simply just add on the number that you're modding by, but to guarantee that it'll work, you need to make sure that everything is positive for things to work nicely, because if things are negative, it doesn't make as much sense as modular arithmetic does. So here we're dealing with...
Just real quick, you might want to minimize your whiteboard again.
Yeah. I am good at streaming, yes. So, the problem with hash values is it doesn't matter what you do, you cannot guarantee that there won't be a collision. You can't really guarantee. Like, there's some tricks in that if you use really, really large prime numbers as your modular arithmetic, you get some nice properties where it's very, very, very unlikely that you'll get a collision, but it's not impossible. So to guarantee that we get a correct solution, so that's the important thing, we always want a correct solution before a more efficient, because we could have a more efficient solution and simply just say, hey, the hashes are exactly the same, that means we must have a match, sweet, return that number. That wouldn't be entirely correct. So what we do is, if we have identical hashes, we go in and manually check as we did in the naive method, just to make sure that we get a proper match. Also, I apologize for the bus that just went by. It's very inconsiderate. So, if we have different hashes, we know that they must be different. If we have identical hashes, they could potentially be different, but we have to go in and check. And we have now, in the best case, in which we have no collisions, we've reduced ONM to effectively ON, but because we have to do the comparison, because we want to be guaranteed of that correct solution, it's not really O(n). But still, a reduce of a factor of n, definitely helpful, definitely better. So once again, we're just going to go over that fact that collisions, there's always going to be, because there will always be a larger, as the slides say, there'll be a larger number of strings than there are possible integers that you need to store. So as the slides measure, a common technique for proper implementations is choosing some whatever number you want that's close to 10 to the 9 so that everything will fit inside a long. So logically, the larger you make your modular thing you're using to apply modular arithmetic, the less likely you are to have a collision. But we also want this to be architecture performance, so we will choose something that fits into a long, and we kind of want to choose that to be preferably want to choose that to be a prime. And so I can't remember the prime that fits into a largest prime that fits into a long off the top of my head, but you should look that up, put it in your code book in case you ever have to use it, because it's just a good number to have there.
So just as a note for implementations there, so you don't actually want to use the largest modulo that fits in a long, otherwise you can't calculate fast exp functions, because you need to multiply by something that is also moduloed by that modulo. So instead what you want to do is use something that fits into 32 bits, or use a modulo that's like within 32 bits, so that when you do the multiplication, which is essentially just a lot of bit shifts, it fits within 64 bits. So as the easiest one to remember is 10 to the 9 plus 7.
Thank you very much, Seamus. I completely forgot about that. Just forgot that. Because, yeah, theoretically you just always want to choose a prime, because primes are nice numbers, and yeah, it's good. So the next algorithm we're going to cover is probably one of the more, I would say, common string algorithms that is perhaps intelligible. So it's almost magic in that it's very cool. And essentially this is solving more the other problem that we had from our naive method, that this is trying to extract as much information as we can from the shifts that we've already looked at. And it kind of looks like a finite state machine, where if we match certain specific characters, we move forward in our matching sequence. If we don't match them, we move back, or we move forward a different amount. And everything is really dependent on what we call the prefix function. Now, I've written a description of what the prefix function is, perhaps more formally. That doesn't really make much sense to me, so we're going to go through an example. So essentially what the prefix function is it's the longest prefix of our string. And by the way, we're only really looking at the prefix function for a pattern, because we're wanting to move along our output string by a certain pattern amount. So it's the longest, let me go back. It is the longest prefix that is also a suffix. Is that right, Seamus?
That is right.
But and depending on your definition, it's the longest proper prefix that is also a suffix, or it's the longest prefix that is a proper suffix.
So just to be a little bit more precise, it's the longest prefix of your pattern string that's also a suffix of the substring from 0 to the index of the character you're searching. Oh, sorry, of the pattern string. My bad.
Yeah. So you can see an example, an example prefix function for this one, in such that the prefix the length, so the length is in the second coordinate of the tuple and what position of the string. So the first coordinate, there is no proper prefix that is also a suffix. Same for 2, 3, 4, and I think I just like to come to this table here because this helps a lot. So if we remember our target string, if we look for we consider a substring of length 1, We have no possible proper prefixes, like the empty is trivial, but that's not proper. So we have a length of 1. For the second one, we have AB. So we have a prefix of A, and that's not a suffix of our string at the moment. We then have ABB. We have 2 possible proper prefixes that we consider. None of them are a suffix of the string we've considered first. 4 is where things get interesting. We have those 3 prefixes we can consider, ABB, AB, and A, and A is actually a suffix of our substring at the moment. So we have a length of 1. Then for 5, you'll see that AB is also a prefix and a suffix of that substring. And say for 6 and 7, we don't get any better than that. So that's an example of what our prefix function would be. And in actual implementations, this last column K here is just represented as an array, not this function we see here before. So here's some code for how KMP works, and the real logic of everything occurs inside the while loop. Now, I think Seamus was angling to explain this logic perhaps better than I was planning to explain it. So, would you like to go ahead?
Oh, sure. Okay, so the idea of KMP, and the reason why it's actually better than n squared, because trivially we see 2 loops here. We see that the loops are essentially going from the start to the end, and then we're also doing a shift inside. It sounds like something very similar to the naive method. However, the thing to realize is we're not actually shifting. We're not just shifting like our starting points that we're doing our search from. We're shifting our entire search window. So our window of search is going to be the length of our pattern string, and every single time you go to a new point in your failure array that you've calculated from your prefix string for KMP, you're shifting your window by that to that point in the failure, like that the failure string points to. So in the worst case, for any string matching algorithm, it's when you have all the characters being the same character. So for instance, you need to find the pattern AAAB in the string of just 64 A's. So in this case, with the naive algorithm, it'll keep on failing at B. But what happens with KMP is when it fails, it then checks A, and it shifts your window along by 1, and then it checks B again, and it shifts along by 1, and so we inch further and further towards the end. So we end up only ever actually computing 2 times n operations for our actual search, which obviously ends up being O of n when we take away the constant time factors. We take away the factors of complexity. And that's essentially the intuition behind it. The exact way it works is through being a finite state machine that goes to that basically moves your search points by the amount that you've already calculated through your prefix suffix array.
Yep, that is pretty good description of how KMP works, and you can see it codified on the slides here, and it's basically we're using Q once again to represent at what point in our string, in what point are we checking in our pattern, what point are we checking at, and so you'll see at the last point, if the point that we're checking is equal to the length of our pattern, we found a result. If it's equal to the current length we're at, we just need to move along by a whole bunch, so that's moving across on the failure, and this is the while loop is the moving across based on the failure, which is all very good. So as Seamus indicated, we have a pretty nice complexity. So computing the prefix function, we have to go over the pattern n linearly to create the prefix function. So that's just going to give us an O(n) time. And then to actually search our input string, that's just also linear. So overall we get O(n) plus m, which is much better than our original m squared or n squared algorithm. Much better. Now, I will make a point here that say that there are algorithms that give not better complexity, but better average case complexity for common cases, such as Boyer-Moore, which uses a very interesting heuristic-based approach on how to move around strings in various ways. But there are a couple of methods for just guaranteed overall linear time, which is what we're about to get into, which is magic, and that is the Z algorithm. And this is a very, perhaps not complicated, but very clever algorithm for going through strings, and Seamus has managed to understand a way to explain it, and I have not, so I'm going to hand it over to him.
Okay, yeah, just jump to the next slide, I guess. I haven't really gone over the slides in a huge amount of detail, so I'll try and use them as a reference, but I also want to kind of talk about the way I think is most intuitive to approaching this. So first of all, what is the Z algorithm? Well, the Z algorithm basically, it creates an array, which each element in that array will store the length of the length of the substring that starts at I in the string and is equivalent to the prefix of the string. So for instance, if we had a string that was AAB, its Z array would be, we don't care about the first element because obviously the prefix starting at 0 will always be the length of the string, so it's not a very useful term. So we always start at index 1. And for AAB, we'd have firstly a prefix of A being equal to A. AB is not equal to AA, so we end our search there. So it's 0, 1, and then B is not equal to A, so it's 0. So our Z array would be 0, 1, 0. Go next slide. This is a little bit...
Yes, wonderfully.
I hope it makes the points that it does. Okay, cool. Yeah, so this is a better example of what I was trying to illustrate without visual prompts. So in this case, we have a string, and every entry in our Z array is counting the length of the prefix starting at the ith position. Calculating the length of the substring that is the same as the prefix. If you're looking at the substring starting from the ith position, traveling to I plus Z of I. So a good way to demonstrate this with this example is to look, firstly, we notice that for the 0th position, again, it's a don't care. We don't care because it will always be the length of the array, no matter what, the length of the string, no matter what string it is. So for index 1, C is not equal to A, so it's 0. For index 2, B is not equal to A, so it's 0. For index 3, we see that AC is the longest string before it's cut off by D, because D is not equal to B, so we enter 2, and we keep on looking at it in this way to end up with our total Z array. Can we go next slide?
There we go.
Cool. All right. So now that we, is this the right one or?
I'm pretty sure this is
Sorry, a lot of slides went past. Okay. So
Wonderful
yeah, so the naive idea of how to construct this Z array is through this idea of like character by character comparisons. So if we do that, that'll be up n squared, and we don't really care about n squared. We have a lot of other solutions that have n squared that are very useful. Sorry, that are much easier to implement. And we have other solutions that are far better complexity. So it's not a very interesting thing. So we don't want to compute this in n squared. And we'll cover how to implement that in not n squared in a bit. But I think before that, just judging by the arrangement of the slides, I might cover exactly how you use this algorithm. So how do you make use of the Z array that we create? Well, what if we put the string that we're searching for at the beginning of the string that we're searching? So we now have a concatenated string. So for instance, if we were searching for, if we were searching for string ABC in this large haystack, then we would simply prefix the large haystack with ABC and construct a Z array from it. And so it's easy to see that for anywhere, for any index that's not within that prefix, but has the length of at least the prefix, you find a pattern match. And so if our challenge then becomes, can we calculate the Z array in linear time? And if so, then our time complexity trivially becomes whatever the length of that concatenated string is, which we know to be O of n plus m. So I believe this is going through the implementation of how to do it linearly. But yeah, so can we just go next slide to check if that's the direction that this is going in, because it seems to have skipped something.
I think it's this.
Okay, yeah. Yeah, so our basic idea behind how to do this linearly is if we're traversing along, if we're calculating how long the prefix of the last string was, then we basically end up with two cases. So we either end up with the case that the index that we're looking at has already been visited, or we don't. So if it hasn't been visited, we can just use the trivial case to look further in the array, so further in the string, and we calculate a longer prefix, and then we store that bound. So we store where we get up to, and if that is greater than where we were before, which it very much should be because that's the only time we use this, then we'll also set our lower bound to be the index that we just calculated. So can we go next slide?
Yep.
Ooh. I feel like I've skipped a line of logic here that I saw that I think we got skipped over. But basically the critical thing to notice is that if we have some lower bound L, then we only need to compare, we know that we already know that A take L will be the same. Essentially, that's like the thing to notice. Oh yes, this is the slide that was missing. Okay, so yeah, if K for Z, K take L is less than R, then we know that Z of K is already Z of K take L. So that's already done. So that's a constant time operation, and then after that, it's just linear time for computing the rest of it, essentially, because so the linear time operation will be the trivial case, so we have to actually traverse the rest of the array. but if we store the lower bound and store the upper bounds, and we know that our current kth position is within those bounds, then we already know that like k plus z of k will be z of k take L. That's already being computed for us. That's a constant time operation. All right, we can probably skip pretty far now, because now we've solved the critical problem. We have a linear time way of generating our z-array, and we have a way to use our z-array to pattern match by taking the string that we were searching for and inserting it at our prefix. So now any value that has the length of our prefix that wasn't actually contained as one of the elements of our prefix, therefore must be a match. Cool. I don't really have anything more to say about the Z algorithm. That's about it.
So I think a few points that I'll just mention on the Z algorithm versus hashing is the Z algorithm is very good for scenarios where you have much smaller patterns compared to the length of your input string, whereas hashing is much more efficient for large patterns compared to the size of the string, because you'll have to do less hashes as opposed to a full linear time sweep. So as the slides say, there's the choice between using a hashing, which is good for large patterns and approximately sized input strings, and then for more smaller strings, the Z algorithm is better.
Cool.
And yeah, as it says, the Z algorithm is, it's not more difficult to implement than hashing, really. It's less complicated techniques, but it's much harder thinking wise, and as it says, not every problem. Z algorithm isn't a silver bullet. String algorithms isn't just one silver bullet. But basically, what it's really good at is pattern matching, and pattern matching in ON time is pretty nice. If you want to see an example implementation in our favorite language, not Python, here you go. Once again, it's two loops, but we're getting linear time complexity now, as opposed to n plus m as we did in KMP.
Yeah, well, we're still getting n plus m. It's just our n plus m is our string.
Yeah, true. Well, yeah, it's still n plus m, but yeah. This one is still slightly better. So I think the last thing that we're going to quickly mention today is tries. And tries are a graph-like structure for storing strings, and they're very cool. So if you've been to Seamus's DP session and my graph theory session, you should be well acquainted to what graphs are and what directed graphs are. And so now we're just going to apply all that to strings. So essentially, as it said, trie is a rooted tree. So if you've been to Seamus's tree algorithm sessions, this should be making even more sense. And the key point is that it's not just one linear long linked list in which there's no real differentiation between an array, is that if strings share a prefix, they can share a chain in the tree. And also, just as a point of note, everything is terminated by a non-alphabetic character. So here is one particular example. We have a start string for the first character. We have two options. We have C or T, and then it diverges each time. You can either consider it as it has the same prefix, or you can consider it at what point do the characters diverge between two strings, is another way of looking at it. Except and you'll notice that even though they have the same prefix, we're using this star here to denote the end of one particular string, and the other one continues on, which is a nice way of looking at things. So the nice thing about tries is that checking if a try has a string of a particular length is linear time, which is pretty nice, and adding new nodes is also linear time, which is not the best if you're familiar with binom or not binary heaps, dynamic heaps and stuff like that. It's not the best insertion time, but it's still pretty good for the benefits that we get from it. So the implementation specifically that we have here is it's just a two-dimensional array with the maximum number of nodes and the size of the alphabet. And the nodes are ordered, obviously, as would be in the list. And it's much like a linked list, in which we just simply just have, if a try exists, we just have a value in that section in the array. Seamus, have you got a more logical way of explaining this particular way of building tries?
Yeah. So whenever you're building a try, it's basically a DFS along along where you expect to be next. So, for instance, you're starting at the root and then looking whether an edge exists with a letter. With the letter that you're at. If it does, then you can traverse along that edge, and you don't need to do anything. You then go to your next letter and see whether that edge exists. Whether it does or not, so say this time it doesn't, you then need to create the try node that has the edge pointing to it from its parent node that's along that letter. And then finally, once you've created all those nodes or traversed sufficiently within the try, you insert either an end of word character, which is normally the way that tries are abstractly presented, or more implementation wise, you typically have a value within your try node that you use to store end of word. And end of word says that, all right, if you've traversed the try up to this point, there is a word here. So for instance, if we were inserting the, when there was already there existing, we would get to the node pointed to by E and set the node's value to be, set the node's end of word value to be true.
Very nice. Very nice. So, this is actually the last slide that we have for this thing. I thought there was going to be another one. But
I'll just talk a little bit more about tries, because tries are actually a really, really interesting data structure. So the idea of tries is they compress like perfect searches, but they compress like searches in general. So tries don't just have to be on the alphabet, they can be or on the numeric alphabet, they can be on any alphabet. And that's very similar to all the concepts that we presented today. We've pretty much universally assumed a standard ASCII alphabet, not really going much further than that. But for instance, a really nice use of tries is typically in bitwise tries. So representations of many numbers by that are visitable in logarithmic time, or like verifiable that they're in the set within logarithmic time, because you just need to go along each bit of the number and traverse its corresponding try node. And if that doesn't exist, then you know it's not in the set. That's a simplification of log base 2. You can see as your alphabet increases, you can compress your search down to log base the size of your alphabet. So tries are an incredibly efficient structure in that regard. The issue then becomes the implementation on how you actually verify that an edge is within a node. And that's normally solved by hashing, which is a constant time operation. amortized, but if you wanted to not use hashing, then the best you could do is logarithmic, in which case your complexity becomes log base alphabet size times log of alphabet base 2. There's lots more about tries, but I think that's enough for now.
Yeah, tries are very interesting, as Seamus has said. Tries are a very, very interesting structure that turn up in lots of different places that you wouldn't expect, and there's a lot of algorithms that are built off of them. My main thing about tries is it's often a decision of whether the complexity to build one is worth the efficiency you gain in the queries as opposed to not building it. And that's normally the decision that it comes down to. But
Yep.
Aside from that, I think that's string algorithms for today. So for those of you who showed up, thank you very much. Thanks, Alden, for showing up. Yes, so in terms of comparison of Z algorithm with KMP, just answering Alden's question very quickly. Z algorithm is more efficient if your pattern is smaller as opposed to KMP. So KMP for small patterns will spend for larger patterns. So KMP will spend more time computing its hash function for large patterns, whereas the Z algorithm doesn't have to worry about that. I'm pretty sure that's the right comparison. And Nick, if you're listening to this, you can tell me otherwise if I've stuffed that up. I believe that's
so the Z algorithm and KMP are almost exactly the same in terms of complexity. So they're both average time 2 times number of operations. It's just those operations are slightly different, so it's all going to be hardware dependent, which is actually faster. It's not actually going to be dependent on the string case as much.
Sure. I don't know. Maybe I'm just thinking a different way, but yeah, wonderful things for looking at strings in different ways. I think.
But yeah, hashing is a whole new bucket of things to go wrong as well as things to go very right.
So I guess it's question dependent. So thank you everyone for showing up. Big thank you to Seamus for showing up and helping me, because definitely needed it for today.
That's okay.
So other than that, thanks for turning up everyone, and we'll see you all next week.